Hello everyone, welcome to a fresh new lecture on efficient algorithms for Fourier analysis, which are nothing but our fast Fourier transforms. This is part of the course Signal Processing Algorithms and Architectures, and I am Dr. Anirban Dasgupta, and let's get started. So, now like in all algorithms, we try to find the complexities. In DFT also we will try to find what are the complexities, or I would say the computation cost. So, we see that this is the equation, and if you perform the DFT in a matrix form, it will be clear. So, if this is our x of n and this is the DFT matrix, which is n cross n, this is n cross 1. So, we see there are n square multiplications. I am not considering additions here because the multiplications are the costliest operations compared to additions. So, what is the big deal in n square computation? Many algorithms have n square computation, but say in a real scenario, we will not compute DFTs of 8 point or 16 point. Typically, we will be interested to compute DFTs which are of very high order. And let us see how with increasing n, this n square term increases, or the number of multiplications increases. So, with 2 we get 4, which is reasonable, 8 we get 64, but as you see we go for higher order DFTs, the number of multiplications are extremely large. And if you are trying to solve a problem like processing my word, say hello. So, if I say hello, say it is taking around say roughly 3 seconds, and if I say my speech is sampled at 48 kilohertz, you can imagine just this hello will have how many samples. And if you do the DFT of the total hello, then you can understand how many multiplications will be required, which is difficult for real time processing. So, can we do better? So, here comes FFT to our rescue. So, the fast Fourier transforms are a set of efficient algorithms to compute the DFT and its inverse. So, what it does, it reduces the complexity of order of n square to order of n log n. Now, if you have studied algorithms course, you know that in divide and conquer methods, we typically reduce an n square complexity to n log n complexity. And to give you a better understanding, let us see that if we are doing n log n and n square, see how much this is reducing. So, as your n is increasing, you see your n square is too much here, but your n log n is still reasonable and it is still quite less compared to n square for a value of 1024. Now, you must be thinking that why I have taken these typical values of n, because when I am going to do this log n base 2 operation, so it will give me an integer if I use these values. So, what makes FFT bring down the complexity from n square to n log n? And the secret behind it is the Twiddle factor. What are the Twiddle factors? So, this e power minus j 2 pi by n. So, this is called Twiddle factor W of n. So, why these Twiddle factors are so important? So, if you see the symmetry property and the periodicity property of the Twiddle factors, they reduce the number of computation immensely, and these two factors help FFT reduce the complexity of the normal DFT algorithm. So, what is the symmetry factor? Symmetry factor means that I just need to compute up to n by 2 or 0 to n by 2 minus 1 points, because from n by 2 to n minus 1, these can be obtained using the DFTs of the first half, and this is by the property. You can easily verify this. So, just try this as a take home assignment. So, just plug in these values and you will see that this is easily verified. Similarly, the periodicity property is also easily verified. Now, periodicity property stems from the fact, as I said in the previous lecture, that these discrete Fourier transforms are considered to be periodic sequences, that is, they range from negative infinity to positive infinity, but we are mainly considering the main period, which is 0 to n minus 1. So, this is just a pictorial representation of the Twiddle factor, which is nothing but, so if you see this symmetry property, so this 7, so of course this is the DC component, and the rest are like these two are like symmetric, these two are symmetric, and these two are symmetric, and this is the middle point, and this is for the real part. If you see the imaginary part also, you can easily verify this property. And periodicity means it is basically repeating. So, I have just repeated for one more period to show you. So, this is n equals to 8. So, this typically repeats, and to understand this, this is the diagram in a complex plane. So, Twiddle factor is nothing but the nth root of unity. So, how do you say nth root of unity? So, 1 can be written as e power j 2 pi. Why? Because cos 2 pi is 1 and sin 2 pi is 0. So, I can just write this as by n and to the power n. So, this becomes the nth root of unity. So, if I plug in n equals to 2, I get my plus and minus 1. If I plug in n equals to 4, I get these 4 points. So, if you draw the unit circle and plot n points on the circle at equal distances, or I would say equal angles, then those are the n roots of your unity. So, if you see this figure, so the symmetry property is very much visible from the plot, and as well as the periodicity. Periodicity means after completing one complete cycle, it will again repeat. So, being of circular nature, it will go on repeating after every cycle, and symmetry is, you can see the symmetry very easily. So, now we will use the divide and conquer approach to efficiently compute our DFT. So, as I said that this direct computation is not using this symmetry and periodicity properties of the Twiddle factor. So, this is what we are interested to compute, the DFT, and in FFT what we will do is we will use a divide and conquer strategy, and the first step is we will divide this DFT into two DFTs, and one way of dividing is one DFT will be of 2 points and other will be n by 2 points, which we will come eventually. But how did this all start? So, it started by factorizing this n into two factors L and M. Now, you might be wondering that what if n is a prime number, what if n cannot be factored easily? So, you can always do zero padding. So, you pad with sufficient zeros to ensure a factorization. The second thing is, so I know that xn is a one dimensional vector or a sequence. Now, what we will do in this approach is, we will map this one dimensional vector 1 cross n into factors L cross M as a two dimensional array or matrix. And why do we want to do this? This will now create smaller signals where we can compute the DFTs of the smaller signals, and we know that if the signal size is small, the computations will be less. So, how can we map this 1D into 2D? Is this a unique way or are there multiple ways? Like for example, if I have 1, 2, 3, 4, I can write 1, 2, 3, 4 as 2 by 2 matrices like 1, 2, 3, 4 or 1, 2, 3, 4. So, accordingly, there can be two possible mappings. One is n can be thought of as capital M L plus small m, where small m varies from 0 to capital M minus 1 and small l varies from 0 to capital L minus 1. Similarly, when we get the frequency is also, instead of an array 1D, we will get a 2D array, like say alpha, beta, gamma and delta. So, we can read this out like row wise, like alpha, beta, gamma, delta, or we can read this column wise like alpha, gamma, beta, delta. So, similarly in frequency also we can have two possible mappings, and here Q and P will be varying according to these indices M and L respectively. If it is confusing to you, let us take a simple illustration. So, here we have this sequence. So, what is M? M is 4. So, small m say varies along this. So, if I say 0, 1, 2 and 3, and L varies downwards 0 and 1. So, what is the value of capital M? It is 4, which means this equation is n equals to 4 L plus M. So, put the M varies from 0 to 3, small m. So, put, and L varies from 0 to 1. So, if L is 0, so M is 0 is this value, M is 1 is this value which is n equals to 1, M equals to 2 is this value, n equals to 2, M equals to 3 is n equals to 3, and then the next value will be L equals to 1 and M is 0. So, that makes n equals to 4. L, then M is 1, L is 1, that is n is 5. Then M is 2, L is 1 and n is 6. M is 3, L is 1 and it is index 7. So, you see what I am doing is I am technically arranging this x n row wise. First row is 2, 3, 5, 6 and the second row is 9, 1, 4, 7. Another way is I just do it column wise like 2, 3, 5, 6, 9, 1, 4, 7. Similarly, the frequencies which I get, I can read out column wise like this, or I can read out row wise this and this. Now, if you have got this idea clear, let us start with the algorithm. And as I said, depending on the arrangement, I can have two such algorithms. So, the first algorithm is we will store the signal column wise. Column wise means say this like this. So, then what we will do? So, we will compute the m point DFTs of each row. So, this is the signal stored column wise and this is the formula to find out the m point DFTs. So, for n point DFT we know the computation complexity is n square. So, for m point DFT it will be m square, and how many such DFTs we are computing? There are L rows. So, L such DFTs we will compute. So, the cost will be Lm square. Now, this signal which I get, I say this matrix is FLQ, and we will multiply with the factor, Twiddle factor WNLQ to this output f of LQ, and this I say this is G of LQ, and this is just multiplying two matrices. So, it will be a cost of L into M. What's next? Next is now this GLQ we will do the L point DFT of each column. So, again as I said, L point DFT will take L square computations or multiplications, and we are doing m such DFTs. So, cost will be ml square, and finally we have got this matrix X which is the DFTs, just we need to now read out the values. Now, I say that considering these multiplications, the storing the signal column wise and reading the values row wise is negligible computation. So, we will not consider these are kind of constant operation. So, if you just read out the values row wise, so we will get the final DFT, and if you verify it will be the exact x of k, which we will get without doing so much things. We will just directly do the computation of the endpoint DFT. Now, you must be thinking that here we are doing lot of computations. We are first doing the endpoint DFT of rows, then multiplying with a rectangular array, and then L point DFT again of the columns. So, won't it be more computations? Well, maths will give the answer, and if I add these three like Lm square, Lm and Ml square. So, if I take Ml common, it is L plus M plus 1. So, 1 does not count in complexity. So, it will be n. So, M into L is n, because that is the factor we had done. So, n times L plus M, which is less than L square, and you check with different values of n. Say if you take n equals to 30, check 30 square, and if you factor it as 6 plus 5, so into 6 plus 5. So, 30 square is 900, and this is 11 into 30, which is 330, much less. So, these are the two algorithms. So, if you feel it complex, because when you will be doing, you will, if the sequence is big, because smaller sequence you can directly find the DFT, it will not matter hardly. As we can see in the n versus n square plot. So, if n is very small, it is not a big issue to do direct computation, but if n is big, then you will probably not do it in hand, you will be doing it in a computer. So, you just remember these steps, because rest are formulas which I have already discussed. So, algorithm 1 is store the signal column wise, then find M point DFTs of the rows, compute G, compute L point DFTs of the columns, and read the DFT values row wise. And the second algorithm is you store the signal row wise, compute L point DFTs of columns, compute this matrix G, then compute M point DFTs of rows, and then read the values column wise. So, another very easy technique to remember is column wise storing the signal, DFTs of rows, then DFTs of columns, and reading DFTs row wise. So, there is an alternate fashion. Similarly, if you store the signal row wise, first do the DFTs of the columns, then do DFTs of rows, and then read the values column wise. So, if you have understood this divide and conquer approach, then it is very easy to understand the most common form of FFT, which is the Radix-2 FFT, or it is also called the Radix-2 Cooley-Tukey FFT algorithm, based on the two computer scientists Cooley and Tukey. So, what is this? So, suppose if I say n is highly composite and it is made up of lot of factors of r, such that it is r to the power v, then such algorithms will be called your Radix R algorithm, and if this r is 2, it is called the Radix-2 algorithm. Now, why this is efficient, we will come to know very shortly. So, first what it will do, so here also L into M, so one will be n by 2 and the other will be 2. And what is the speciality about 2 is that if you see the 2 point DFT, it is just adding and subtracting. So, you do not need any difficult computation in that, you just need to add the values to get capital X0, and the difference of the values will give you the capital X1. And then again this n by 2 can be further divided into n by 4 into 2 and into 2, and in this way you keep on doing unless you are computing all 2 point DFTs. So, to start with, as I said, M is n by 2 and L is 2, and here n will be, small n will be varying from 0 to n by 2 minus 1. So, essentially what are we doing? We are taking the even samples and the odd samples. So, if I have signals like 3, 2, 1, 6, 0, 2, so this will form my first subsignal F1n, and this will form the second subsignal F2. So, what are we doing? Essentially, we are skipping some values of the signal and forming the sub-signal, and this process is called decimation or downsampling. So, there is a difference between decimation and downsampling, which we will cover in multi-rate signal processing, but as of now understand that since we are skipping some signals in the time domain, this is called the decimation in time algorithm. And just to clearly explain the mathematics, so this is my original formula of DFT, where I say this is for the even values of n and this is for the odd values of n. So, even values, I replace my n as twice m, n equals to twice m, and this is for the even values and this is for the odd values, the two small DFTs we are calculating. And now we will use some properties, like we know Wn square will be Wn by 2. So, here we will put down the DFT matrix to n by 2. So, which is meaning we are halving the size of the DFT matrix, and this is very evident from the calculations. So, this x of k, which is an n point DFT, is broken down into two DFTs. One is of length n by 2 and the other is also of length n by 2, and this is the multiplication with that Twiddle factor, which is giving that g thing in the divide and conquer approach. Great. So, now we have two n by 2 point DFTs again. So, this case our k, since this is n by 2 point DFT, now my k will be varying from 0 to n by 2 minus 1, but we need the values from n by 2 to n minus 1 also. Now, here comes my symmetry property. So, the rest, since it is symmetric, so we will use the symmetry property, and with this we can extend this to the other half of the DFT, and we keep on doing this, as I said. So, from n we get 2 n by 2 point DFTs, then from n by 2 we get 4 n by 4 point DFTs, and we keep on doing until finally we end up in 2 point DFTs, and 2 point DFTs, as I said, is just adding and subtracting. So, what is essentially the computation? So, we have to do these n values, that is the n thing, and then the height of the tree, if you see, so every time it is halving itself. So, this height will be log of n base 2, and hence the complexity is reducing to n log n base 2. So, the two algorithms, so this is called a butterfly diagram, because somewhat looks like a butterfly wings. So, this is the decimation in time algorithm. How would you understand? See the input side. So, input side, the first sample is x of 0, then 3 samples are skipped, x1, x2 and x3, and then I get x4. Similarly, I get x2 and then I skip 3 samples, I take x6. Then I take x1, skip 3 samples, take x5, and similarly take x3 and then skip 3 samples, take x7. Now, why 3 samples? Because there are 2 stages. So, each stage is dividing into half of the previous stage, like a recursion kind of a thing, or you can consider this as storing the DFT values column wise. So, this is just like x, if you see x0 coming here, then x1, x2, x3, x4, x5, x6 and x7. So, this is going to be the first DFT. We are doing the DFT column wise, right, and in the frequency we will read it sequentially. The other version is the decimation in frequency or DIF algorithm. This is also the butterfly diagram, and here we will take like the reading, store the signal row wise like as it is, but when we will read the frequencies, we will read them column wise. So, here we see that the frequencies are decimated. So, we have to see this and then we will get this. So, that is the decimation in frequency algorithm, and the remaining thing is self-explanatory. This is just multiplying with the Twiddle factors as per the formula, and this is just a simple signal flow graph. So, just these two are the pictorial representations. This is for an 8 point FFT and this is for a 16 point FFT, which is 3 stage. So, thank you so much. We will meet again in the next lecture.